Welcome to the API 571 Audio Masterclass series. This episode is brought to you by Mag Integrity. For the complete high-resolution study guides, API 571 exam prep question banks, and to unlock our full private audio library, visit our premium engineering portal at magintegrity.ca.
So if you put yourself in the shoes of a turnaround inspector for a minute.
Okay.
Yeah. You're standing on scaffolding, maybe 70 feet in the air, and you're staring at a 4-inch ASTM A53 reflex line on a fluid catalytic cracking main fractionator.
Just a standard overhead line.
Exactly. But this specific line has been in service for 52 years.
Wow, half a century.
Half a century of continuous operation. And visually from the outside, the pipe looks, well, perfectly fine.
No obvious wall loss or anything?
Right. Thickness readings are completely solid. Operations logs show normal parameters for decades. But hiding just beneath the surface, parallel to a circumferential weld, is this microscopic intergranular spider web that is just tearing the steel apart from the inside out.
And it's invisible to the naked eye.
Totally invisible. It's not thinning the pipe. It's not creating a massive bulge. It's silently unzipping the grain boundaries of the carbon steel, basically just waiting for one minor pressure transient to fail catastrophically.
Which is pretty much the ultimate nightmare scenario for asset integrity.
Oh, absolutely, because you're dealing with a failure mode that actively defies our standard expectations of corrosion. We are so conditioned to look for, general wall loss or pitting or obvious acid attack.
Right, the stuff you can see and measure easily.
Yeah. But alkaline carbonate stress corrosion cracking, or ACSCC, it just doesn't behave like a conventional corrosive mechanism. It's highly localized, heavily dependent on residual stress, and it requires this incredibly fragile, almost contradictory set of environmental conditions to even initiate.
So for this deep dive, we really need to dissect the parameters of carbonate cracking. Because looking at the source material, the industry guidelines are extremely rigid on this.
They really are.
Like, you need a mandatory chemical trifecta for this to happen. A free liquid water phase, carbonate ions, and some amount of hydrogen sulfide, H2S.
Yeah, and if you remove even a single element from that equation, the entire mechanism just arrests.
It stops completely.
Completely.
Yeah.
The requirement for a free liquid water phase is absolute. We aren't talking about high humidity or steam vapor here.
Right, it can't just be a gas.
No, there must be a physical condensing liquid water film in direct contact with the steel, because that liquid water acts as the electrolyte.
Oh, okay.
Without the electrolyte, the specific localized anodic dissolution required for the cracks to propagate simply cannot occur. Period.
Okay, so you have the water, then you introduce the carbonate ions and the H2S into that water phase. And the presence of H2S is super interesting here because I think when most field engineers hear H2S and cracking, their minds immediately jump to, wet H2S damage.
Oh, yeah, sulfide stress cracking or hydrogen-induced cracking.
Exactly. But ACSCC is fundamentally different, isn't it?
Yeah. It is. We aren't dealing with hydrogen atoms diffusing into the steel lattice and causing embrittlement. That's a totally different physical process.
Right, because this is an anodic dissolution mechanism.
Yes. The H2S is playing a completely different role here. It's acting as a catalyst for the breakdown of the steel's passive armor.
Okay, break that down for me. What do you mean by passive armor?
So under standard sour operational conditions, carbon steel and low alloy steels aren't, completely defenseless. They react with the environment to form these microscopic protective surface films.
Like an oxide layer.
Similar, yeah. Specifically, they form iron carbonate, iron sulfide, or complex iron oxides. And these films normally passivate the steel surface. They significantly slow down any further corrosion.
Right, the steel basically protects itself.
Exactly. But the specific local chemistry of alkaline carbonate water combined with H2S, it creates a highly aggressive localized environment. The thermodynamics shift completely.
So the fluid just constantly attacks those films.
Yeah, it continuously strips away those iron-based films.
If the steel is trying to protect itself by forming these iron carbonate or iron sulfide films, what exactly is stripping that armor away faster than it can heal?
It's essentially a repassivation kinetics issue. The steel is trying its hardest to heal itself by precipitating a new iron sulfide or iron carbonate scale. But the local environment is just dissolving that scale faster than it can form.
I see. So it's like a biological scab on a wound.
That's a great analogy, actually.
Yeah, you have this scab forming in a highly caustic environment. The scab forms, but the environment just eats the edges away before the skin can fully heal.
Yes. And because the component is under mechanical tension, the underlying grain boundaries are constantly being exposed. The anodic dissolution, which is the actual dissolving of the iron matrix into the electrolyte, it concentrates precisely at those exposed grain boundaries.
And that concentrated dissolution is what dictates the morphology of the damage, right?
Exactly. ACSCC is strictly intergranular. The crack propagation doesn't just shear transgranularly through the crystalline structure of the ferrite or pearlite grains.
It goes around them.
Right. It snakes its way along the grain boundaries, essentially dissolving the atomic glue that holds the crystals together.
That sounds terrifying.
It is. Under a microscope, this creates a highly branched, intricate network of small cracks. It looks exactly like shattered safety glass or a spider web on the surface of the metal.
And the text notes that it heavily favors initiating at existing weld-related flaws, which makes perfect sense from a fracture mechanics perspective, doesn't it?
Oh, absolutely. I mean, think about a minor weld undercut or a bit of lack of fusion or even a microscopic slag inclusion.
Those aren't just defects, they're massive stress risers.
Exactly. They act as anchors. The protective film is much more likely to rupture at the apex of a stress riser because of the localized microstrain.
Right, because all the physical tension is focused right on that tiny point.
Yeah. And once the film ruptures at that tiny crevice, the localized chemistry within the crack tip becomes even more aggressive than the bulk fluid. It drives the anodic dissolution deeper and deeper into the web of grain boundaries.
Which naturally brings us to the material itself. The documentation establishes that carbon steel and low alloy steels are the primary susceptible materials here.
Correct. But it's really important to note that it's not a blanket vulnerability across an entire piping system. You aren't going to see this just anywhere in a straight run of pipe.
Right. The damage is overwhelmingly localized to specific physical zones, zones where mechanical energy is permanently trapped in the steel.
Yes, we are looking almost exclusively at welds and severely cold-worked areas.
Let's break down the spatial parameters around those welds, because the industry guidelines define some very specific boundary limits.
They do. Cracks typically propagate parallel to the weld, and they manifest either directly in the weld deposit itself in the heat-affected zone or in the adjacent base metal.
But there's a definitive 2-inch danger zone, right? Like 50 millimeters?
Yes. The cracks are usually contained within 2 inches of that weld seam.
Why 2 inches specifically?
That 2-inch boundary is a direct physical manifestation of thermal residual stress. When a circumferential pipe weld is deposited, the localized area is elevated to the melting point of the steel.
Right, obviously.
But as the weld pool solidifies and cools down to ambient temperature, the metal undergoes severe volumetric shrinkage.
It shrinks as it cools.
Exactly. But that cooling weld is physically restrained by the colder, solid pipe on either side of it. It cannot shrink freely.
So it's basically locked in a tug-of-war.
Precisely. And as a result, massive tensile residual stresses are locked right into the metallic matrix.
Wow.
The peak of this tensile stress occurs in the weld metal and the immediately adjacent heat-affected zone. Then, the stress gradient gradually dissipates as you move outward into the base metal. By the time you're 2 inches away from the weld toe, the residual tensile stress has generally dropped below the threshold required to drive the intergranular cracking.
Okay, that makes perfect sense for a weld.
Yeah.
But the guidelines explicitly contrast that standard 2-inch rule with a major spatial paradox.
The cold work fittings.
Yeah. When we look at highly cold-worked fittings, specifically elbows and reducers, the cracking behavior changes completely. Documented failures in these components show cracks extending more than 3 inches or 80 millimeters away from the weld.
Yeah, it's a huge difference.
A pipe elbow isn't seeing the intense, localized thermal gradient of a weld. So why does the danger zone suddenly expand so dramatically in these fittings? It makes sense that the heat-affected zone right next to the weld is vulnerable, but why do elbows extend that danger zone out past 3 inches?
Well, it comes down to the fundamental difference between thermal residual stress and mechanical residual stress.
Okay.
Think about manufacturing a carbon steel elbow or a reducer. You're taking a straight section of pipe and forcing it into a new geometry through severe plastic deformation.
You're physically bending it into shape.
Right. And unless this is done via hot forming above the recrystallization temperature or followed by a full normalization heat treatment, you are cold working the steel. You are permanently distorting the crystalline lattice across the entire body of the fitting.
So the whole thing is just loaded with stress.
Exactly. This process traps an immense amount of stored mechanical energy tensile residual stress throughout the entire macrostructure of the component.
So the entire fitting is just sitting in the unit, like a loaded spring.
That's a perfect way to visualize it. A weld only loads the spring within that 2-inch thermal gradient. But a cold-worked elbow is spring-loaded across its entire geometry.
Oh, wow.
So when the alkaline carbonate fluid breaks down the surface film, it doesn't just find localized tension near the weld. It finds sufficient mechanical driving force 3, 4, or even 5 inches away along the extrados or intrados of the elbow.
So the stored mechanical energy just physically pulls the grain boundaries apart as the anodic dissolution eats away the bonds.
You've got it. That's exactly what happens.
If carbon steel and low-alloy steels are this vulnerable to cold work and welding in these environments, the immediate engineering response is to look at alloy upgrades, right?
Always.
And the documented upgrade paths include solid or clad 300 series stainless steel, alloy 400, or other corrosion-resistant alloys.
Yeah, and by upgrading to a 300 series austenitic stainless steel, we are fundamentally changing the surface chemistry. We are no longer relying on a fragile iron sulfide or iron carbonate film.
Right, because stainless has the chromium.
Exactly. We are relying on a robust chromium oxide passive layer that simply does not break down in the alkaline carbonate environment.
So it just shuts the whole mechanism down.
Completely. The electrochemical cell that drives ACSCC is completely neutralized by the chromium and nickel content in those higher alloys. The mechanism requires an anodic reaction that is specific to the iron matrix in an alkaline solution.
Okay, so we've established the metallurgy and the stress requirements. But the environment is the actual trigger.
Right.
Let's really dig into the operational variables, specifically the water chemistry. We know we need liquid water, carbonates, and H2S.
Right.
But the operational threshold that dictates the severity of this cracking is highly dependent on pH. Industry data raises a massive red flag when the sour water environment reaches a pH of 8.0 or higher.
And this is a critical paradigm shift for many operators, honestly. We traditionally associate high corrosion rates with low pH.
Right, highly acidic environments.
Exactly. But ACSCC is an alkaline mechanism. The vulnerability of the protective iron-based films flips at higher pH levels.
So it's the opposite of what you'd intuitively think.
Yeah. In a sour water system, you have H2S acting as a weak acid. But these streams are rarely pure. They contain ammonia, amines, or other basic compounds that heavily buffer the solution.
And that drives the pH up.
Right. It drives the bulk fluid pH up into the alkaline range, specifically at or above that 8.0 threshold. And at this pH, the concentration of carbonate and bisulfite ions shifts, creating an electrochemical environment that is incredibly hostile to the passivation layer of carbon steel.
Now, the guidelines also highlight a really critical field engineering trap when it comes to actually measuring that pH.
Oh, sampling issue, yes.
Yeah. There is an explicit warning to verify your sampling and analysis procedures before testing highly buffered sour water streams. If we're relying on a pH reading of 8.0 to trigger our inspection protocols, the accuracy of that sample is paramount. Why are highly buffered sour water streams tricking standard sampling and lab analysis?
It is entirely an issue of chemical equilibrium and pressure. Think about what's happening inside the processing unit. The sour water stream is typically at an elevated temperature and an elevated pressure.
Right.
The H2S, the ammonia, the CO2, they're all dissolved in the liquid phase, held in this very delicate pressure-dependent equilibrium that dictates the in-situ pH.
Okay.
But then an operator pulls a sample from a bleeder valve into a sample bong or just a glass jar.
And pressure drops.
Instantly, the fluid is dropped to atmospheric pressure.
And it flashes.
Exactly. The dissolved gases immediately flash out of the liquid phase. The H2S and CO2 escape, the temperature drops.
So the sample is ruined immediately.
The thermodynamic equilibrium of the highly buffered solution is completely shattered within seconds. By the time that sample makes it to the laboratory bench an hour later, the chemistry is fundamentally altered.
Wow.
You might read a safe, neutral pH of, say, 7.2 on the lab report, completely unaware that the physical liquid film actively condensing against the inside of the fractionator overhead pipe is actually sitting at a highly aggressive pH of 8.5.
So you are literally flying blind. You think your unit's perfectly safe based on bad data, while the actual operating environment is actively dissolving the grain boundaries of your carbon steel.
It happens all the time.
Which brings us to the physical refinery impact. Where exactly do we see this perfect storm of high pH, highly buffered sour water, liquid condensing phases, and residual stress? The operational data points heavily toward fluid catalytic cracking, or FCC, main fractionator overhead systems.
Yes, the FCC overhead is basically the textbook environment for ACSCC. You have the catalytic cracking of complex feedstocks, and that generates a massive amount of light ends, H2S, and nitrogen compounds like ammonia.
And then it cools down.
Right. As these vapors leave the top of the main fractionator and enter the overhead condensing system, the temperature drops. Water begins to condense out of the vapor phase. The ammonia heavily buffers this newly formed liquid water, driving the pH alkaline.
So you have condensing liquid water, carbonates from the CO2, H2S, and an alkaline pH. The perfect storm.
Exactly.
And the documented failure points in the guidelines are incredibly specific. They highlight overhead, interstage, knockout, drum vapor, outlet nozzles.
Yes.
But the case study that really illustrates the insidious nature of this mechanism is that 4-inch ASTM A53 reflex line on a main fractionator that leaked after 52 years of service. A pipe surviving half a century before suddenly failing from ACSCC is a massive anomaly that really requires dissection.
It does, and it perfectly highlights that this is an environmentally driven, highly localized phenomenon. It is not a continuous linear corrosion rate.
Right, it wasn't just slowly rusting away for 50 years.
No, that 4-inch A53 line did not have a manufacturing defect that slowly propagated over 5 decades. It was likely exposed to an environment that hovered just below the critical threshold for the vast majority of its life.
We see this all the time with process creep, don't we?
Constantly.
Refineries change their crude slates. A crude with higher nitrogen content will generate more ammonia in the FCC, slowly creeping the overhead pH up over the years.
Or upstream hydrotreating parameters shift.
Yeah, or operations decides to lower the overhead temperature slightly to optimize product recovery. And inadvertently, they shift the dew point and create a persistent liquid water phase further upstream in a section of pipe that had historically operated completely dry.
Exactly. For decades, the residual stress from the original 1970s construction welds sat there completely dormant because the pH was maybe 7.5 or because there was no free liquid water.
But then one small change pushes it over the edge.
Right. The moment the operational creep pushed the local environment over that pH 8.0 threshold and a liquid film condensed, the chemical catalyst was initiated. The surface film broke down, and the pent-up mechanical energy from 52 years ago finally had the avenue to rip the grain boundaries apart.
That is just wild to think about. And then there's the other documented case, an 18-inch diameter API 5L grade B pipe section. This specific section featured 2 1-inch water wash injection nozzles running from the inlet to the second stage compressor.
Right, the water wash nozzles.
Yeah. Look at the common denominators here. Overhead knockout drums, reflux lines, and water wash injection nozzles. The uniting factor is the deliberate or unavoidable presence of free water.
A water wash injection point is practically a manufactured ACSCC test cell. Think about it. You were taking a heavy wall 18-inch API 5L grade B pipe, and you're welding in small, highly restrained 1-inch nozzles.
Which generates massive localized residual stress.
Exactly. Then you are purposefully injecting liquid water directly into a sour gas stream. The water acts as a scrubbing agent, it absorbs the H2S and ammonia, and immediately creates a localized pool of highly buffered, high pH sour water directly on top of the highly stressed nozzle welds.
Wow. So if those welds weren't properly stress relieved, cracking is almost an inevitability.
It's just a matter of time.
So we have these microscopic, intergranular spider webs propagating under the surface of legacy piping and highly stressed injection points. This necessitates a massive pivot into inspection and damage detection. How on earth are inspectors supposed to find a defect that doesn't cause general wall loss and is practically invisible to the naked eye?
Well, the guidelines prioritize a multi-layered approach, and it actually starts with process monitoring.
Before you even look at the pipe.
Exactly. Detection begins long before you put an NDE technician on scaffolding. Routine monitoring of the pH and carbonate levels of the sour waters is the primary leading indicator.
Right, you have to track the chemistry.
You have to aggressively track the unit chemistry. If the process data shows the pH trending toward that 8.0 threshold, or if the carbonate concentrations spike, you know you need to deploy targeted physical inspection to the highly stressed nodes in that specific circuit.
And when you do deploy NDE, the guidelines list several surface methods. Wet fluorescent magnetic particle testing, WFMT, alternating current field measurement, ACFM, and eddy current testing, ECT.
Yes, and WFMT is widely considered the workhorse for finding these surface-breaking intergranular cracks.
But there's a massive, bold print caveat attached to all these surface methods. Proper surface preparation is strictly required, And the warning is really severe. If blending or smearing of the metal occurs during surface prep, it will mask the fine cracks. The text says we need to prep the surface but warns against smearing the metal. If these cracks are microscopic spider webs, how do you properly blast or grind a pipe in the field without accidentally erasing the very evidence you're looking for?
That is the million-dollar question. The physics of surface smearing is one of the most critical field execution challenges in all of asset integrity.
Really?
Oh, yeah. Think about the rheology of carbon steel. It's relatively ductile. And the intergranular cracks caused by ACSCC are incredibly tight. We are talking about hairline separations at the grain boundaries.
Right, they aren't gaping holes.
Exactly. So if an inspector or a pipe fitter takes a heavy, rigid grinding wheel or an overly aggressive, abrasive flap disc to the weld, just trying to clean off the external paint, rust, and scale, they are not just cleaning the metal, they are generating intense, localized heat and lateral friction.
They're essentially plastically deforming the surface layer of the steel.
Yes. The abrasive source literally shears the ductile ferrite phase right over the top of the tight crack opening. It acts like a metallurgical caulking compound.
Oh, wow.
It completely bridges the gap at the surface. The crack is entirely intact and still propagating underneath, but the surface is mechanically sealed.
So you apply the NDE.
When you apply the magnetic field for WFMT, the magnetic flux lines do not leak out of the crack because the smeared metal provides a continuous path for the magnetism.
The fluorescent particles don't gather.
Right, the indication vanishes. And the exact same applies to eddy current. The probe's electromagnetic field just sees a continuous, uniform surface conductivity.
So the inspector signs off on a clean weld, completely unaware that they just buried the very crack they were looking for.
Exactly. It requires extreme finesse in the field. You absolutely cannot use brute force mechanical grinding.
So what do you use?
Surface prep for ACSCC requires light, localized, abrasive blasting, like a gentle sweep blast. Or you use highly specialized, non-loading abrasive wheels that remove oxides without generating the shear force required to smear the matrix. It really requires a technician who fundamentally understands the metallurgy of what they're touching.
Okay, so once you successfully identify the crack on the surface, without smearing it, the immediate operational question is sizing. How deep does the spider web go? Can the unit run until the next scheduled turnaround, or do we need an emergency shutdown?
Right, the fitness for service evaluation.
For depth sizing, the guidelines point to volumetric NDE methods, specifically angle beam ultrasonic techniques, shear wave ultrasonic testing, SWUT, and phased array ultrasonic testing, PAUT.
Yes. The physics of ultrasonics are essential here. You are pulsing high-frequency sound waves into the steel at an angle. When those sound waves hit the highly branched intergranular faces of the carbonate crack, they reflect back to the transducer.
And the software interprets that.
Exactly. By analyzing the time of flight and the amplitude of the returning signals, PAUT can build a highly accurate volumetric profile of how deeply the crack network has penetrated the pipe wall.
The guidelines also note acoustic emission testing, AET, for locating and monitoring crack growth in real time, right?
Yeah, AET is fascinating. You're basically listening for the high-frequency acoustic stress waves that are generated as the grain boundaries tear apart under operation.
But the most fascinating sizing technique explicitly noted in the guidelines isn't an NDE method at all. It is a physical intervention. Grinding out the cracks is explicitly noted as a viable method of crack depth determination.
Yes, it is.
And this is a point that completely contradicts the instincts of many mechanical engineers. With many damage mechanisms like severe fatigue cracking or certain forms of brittle fracture, taking a grinder to an active crack is incredibly dangerous.
Oh, absolutely.
The localized heat input and the mechanical stress of the grinding wheel can act as a wedge, causing the crack to suddenly run or propagate deeper into the material. So why is ACSCC different? Why does carbonate cracking politely stop and allow the inspector to safely grind a divot into the pressure boundary to measure the depth?
It's a great question, and it is entirely due to the environmental dependence of the mechanism. Remember, ACSCC requires the chemical electrolyte, the alkaline carbonate fluid, and the sustained global residual tensile stress.
Right.
When a technician applies a grinder to the crack location, they are physically excavating the crack tip. They are removing the anodic crevice where the localized dissolution is actually occurring.
Oh, I see.
Because this is not a mechanically driven fatigue crack, removing the sharp tip and taking it out of the immediate chemical microenvironment instantly arrests the mechanism.
So the macroscopic residual stress of the pipe might still be there, But you've eliminated the microscopic stress riser and the chemical cell at the crack tip. The anodic dissolution just stops.
Correct. The technician can carefully grind down into the pipe wall, continuously stopping to reapply WFMT, ensuring they don't smear the surface, of course, until the magnetic particle indication completely disappears.
And then you just measure the hole you made.
Exactly. At that point, you physically measure the depth of the excavation, you know exactly how deep the crack penetrated, and you can perform an engineering fitness for service evaluation on the remaining wall thickness.
It is a delicate, high-stakes operation to find them, and literally a brute force physics application to size them. But detection is inherently reactive. The goal of engineering is prevention.
Always.
The guidelines are extremely rigid regarding the mitigation and prevention of ACSCC, heavily prioritizing thermal defense. The primary mitigation strategy is post-weld heat treatment, or PWHT.
And the parameters for this heat treatment are not suggestions, they are stringent metallurgical laws.
Right, the documentation mandates that a stress-relieving heat treatment must be applied at exactly 1200 degrees Fahrenheit to 1225 degrees Fahrenheit.
Yes. That is 650 degrees Celsius to 665 degrees Celsius. And this must be executed in strict accordance with industry standards WRC 452 and WRC 552.
And it applies to everything, right?
Everything. Furthermore, this requirement is absolute across the board. It applies to major construction welds, minor repair welds, and all internal and external attachment welds.
I really want to focus on that temperature band. 1200 to 1225 degrees Fahrenheit. That is a microscopic 25-degree window.
It's incredibly tight.
If you are heat treating a massive heavy wall fractionator spool piece in a shop furnace or wrapping ceramic heating blankets around a field tie-in weld out in the pipe rack, maintaining a delta of 25 degrees across the entire weldment is an incredibly difficult thermodynamic challenge.
It is a massive headache for field crews.
So why is the industry standard so uncompromising on this exact window? What is happening to the atomic lattice of the carbon steel at exactly 1200 degrees that neutralizes the threat of the alkaline carbonate fluid?
It is a phenomenal metallurgical balancing act. You are attempting to achieve a massive structural change without altering the fundamental properties of the alloy.
Okay, walk me through the physics.
The goal of PWHT is to eliminate the locked-in tensile residual stress from the welding process. Residual stress is, at an atomic level, a massive pileup of dislocations within the crystalline lattice. To relieve that stress, you have to increase the thermal energy of the steel enough so that atomic mobility increases.
We have to soften the matrix.
Exactly. You have to elevate the temperature until the yield strength of the carbon steel drops significantly below the level of the residual stress. When the yield strength drops, the locked-in elastic strains finally convert into microscopic plastic deformations.
The atoms actually move.
Yes, the dislocations glide, annihilate, and rearrange. The lattice relaxes. If you do not hit that 1200 degree Fahrenheit minimum, the yield strength remains too high. The lattice does not relax sufficiently, and dangerous levels of residual stress remain trapped, providing the mechanical energy the carbonate ions need to pry the grain boundaries apart.
So the minimum is strictly driven by the required drop in yield strength. But why the hard ceiling at 1225 degrees? If 1200 degrees relaxes the steel, why not just push the furnace to 1300 or 1350 degrees just to guarantee complete stress relief? What's the penalty for overshooting?
If you exceed 1225 degrees Fahrenheit, you move beyond simple stress relief and start driving fundamental microstructural transformations. You begin altering the mechanical properties of the carbon steel base metal.
Get too soft.
Worse, a prolonged exposure above this tight window can lead to excessive tempering, ceratization of the perlite colonies, or even grain growth. You risk severely reducing the tensile strength of the pipe, and more critically, you risk destroying the impact toughness.
Oh. You solve the carbonate cracking vulnerability, but you create a pipe that might shatter under a low-temperature pressure surge because you baked all the toughness out of it.
Exactly. That 25-degree window is the absolute metallurgical sweet spot. It provides enough thermal energy to neutralize the mechanical driving force of the residual stress, effectively disarming the ACSCC mechanism while remaining cool enough to preserve the required structural integrity and impact toughness of the steel.
But the guidelines immediately follow that strict temperature mandate, with a massive, very realistic caveat regarding field execution. It explicitly states that highly restrained welds made in the field may still retain substantial residual stress even after PWHT is properly applied.
And this is where metallurgical theory violently collides with field reality.
Also,
Well, think about a controlled shop environment. A pipe spool sits on a cart in a massive furnace. As it heats up to 1200 degrees, the metal expands freely. As it cools down, it contracts freely. The stress relieves perfectly.
right, there's nothing fighting it.
But now consider a repair weld on an FCC overhead system 50 feet in the air. The piping is heavily bolted to heavy flanges, locked into structural pipe shoes, and tied into massive heat exchangers. It is highly restrained.
It physically cannot move.
Exactly. So when you apply heating blankets to that single field weld and drive it to 1200 degrees, the local metal attempts to undergo thermal expansion. But the macro restraint of the rigid piping system fights back. It compresses the yielding metal.
Oh, I see where this is going.
Then, as the weld cools down from the PWHT cycle, the metal attempts to undergo thermal contraction. But again, it is anchored to immovable components. The piping system resists the shrinkage, physically pulling against the cooling weld.
So the heat treatment relaxes the microstresses of the localized weld pool, but the massive structural restraint of the unit immediately reimposes entirely new macro-residual stresses as the joint cools back to ambient.
Yes. The mechanical physics of the restraint entirely defy the thermal physics of the stress relief. You can have charts proving you held the weld at exactly 1215 degrees for 2 hours and still end up with a weld joint loaded with tensile residual stress.
Meaning it's still fully susceptible to carbonate cracking the moment the unit comes back online and the pH hits 8.0, which introduces a highly provocative engineering debate regarding long-term reliability. If field welds are inherently a wild card, even after executing a perfect, mathematically verified 1200-degree bake, at what point does a reliability engineer stop trusting carbon steel altogether in these high pH foul water systems? I mean, do you just spend the capital on an alloy 400 upgrade?
The guidelines explicitly offer material alternatives for exactly this reason. If PWHT is not viable, use effective barrier coatings or upgrade to solid or clad 300 series stainless steel, alloy 400, or other corrosion-resistant alloys.
It's the ultimate calculation of life cycle engineering economics.
It really is. Carbon steel with PWHT is vastly cheaper on initial capital expenditure. But if you have a highly restrained field tie-in on a critical FCC overhead system, where the historical operational data proves the sour water pH frequently touches 8.5 relying on field heat treatment, is an enormous gamble.
So upgrading to an alloy 400 or a clad 300 series, stainless steel bypasses the mechanical restraint variable entirely.
You change the rules of the game completely. You deploy a material where the surface chemistry, that passive chromium or nickel oxide layer, is completely immune to the anodic dissolution driven by the alkaline carbonates.
Regardless of how much residual stress is locked in the weld.
Right. Sometimes the heavy capital expense of an exotic alloy upgrade is the only definitive way to buy true operational peace of mind. You eliminate the vulnerability by removing the susceptible matrix.
And as we look toward the future of the refining industry, this calculation is only going to become more complex. We are constantly seeing pushes for deeper process optimization. What happens when a facility, aiming to maximize product recovery or increase energy efficiency, systematically lowers the operating temperatures of their overhead condensing systems?
They shift the dew point.
Exactly. They might inadvertently shift the dew point, creating massive, persistent zones of free liquid water in legacy carbon steel systems that have safely operated dry for 30 years.
Or consider the shifting global crude slates.
Right. As refineries process heavier, more challenging crudes with higher nitrogen content, the ammonia generation in the cracking units will inevitably rise.
Pushing that sour water pH higher and higher.
A system that has comfortably operated at a safe pH of 7.2 for decades could slowly creep into the alkaline danger zone. The metallurgical physics don't change, but the operational realities surrounding these aging assets are shifting constantly.
Making the detection and mitigation of this microscopic spiderweb more critical than ever.
That wraps up our technical deep dive on this mechanism. Don't leave your exam or your asset integrity to chance. Head over to magintegrity.ca right now to subscribe to our full premium library, download the Visual Slide Companion Pack, and master API 571. Until next time, keep your assets safe and your inspections rigorous.